Let's do a couple of examples with torques and levers and look at how this works in the body. So first of all, let's look at the bicep. How much force is required to hold the forearm up? I'm just going to draw a cartoon version of this. This is my axis of rotation, which is right here. Now, there is a force that's applied right about here, and I'm going to draw it at 90 degrees. It's not quite 90 degrees, but it's close to it. And this is the force of the bicep, and that's what I want to know. What is the force in the bicep? Right here, this muscle attaches right about here, and it causes you to pull up the forearm when you need to. And we'll say that this distance, I'm going to use inches here, even though it's not the metric system. We'll say that this distance is about 2 inches. And then I want to know what is the weight of the forearm, and that weight is going to be, the weight of the forearm will be right here. I'm going to list it at, or show it at about the center of mass. We'll talk about center of mass next, but just for now, just say that, well, my weight is going to be applied right there. And we'll say that this distance is about 9 inches. By the way, this point right here, is that called your insertion point, or is that called the origin point? Of course, it's called the insertion point. That's the point where it's attached to the bone that moves, which is your forearm in this case. And this weight, I want to estimate what the weight of my forearm is. My forearm is about 10 pounds. You might, if you're really strong, maybe you have a heavier forearm. I'm going to say 10 pounds. That's probably a bit of an overestimate, but let's just run with it. Now, what is the force required just to lift the forearm? I know that the torque on one side has to equal the torque on the other side. That is, the torque due to the bicep has to equal the torque caused by that weight. And so my bicep times that 2 inches should equal to my force weight. Let's see, I'll go and put in a number there. It's 10 pounds times 9 inches. And so that means that the bicep has to exert, uh, 45 pounds in order to lift a 10-pound forearm. Now imagine, what if I have a weight? So I put a weight here, and let's say that it's a 10-pound weight. Now, what is the force required? Well, now I have two forces over here. Show you how this is going to go. My torque on the left-hand side will have to equal the torque on the right-hand side. All right, so the torque due to this has to equal the torque due to these two forces. So now I have two forces that are causing a torque. Uh, on the on the bicep side, I have the force due to the bicep times my 2 inches, that's the distance, and then that's going to equal to the weight of the bicep, that was 10 pounds, times the distance, which is going to be 9 inches, we said, plus another 10 pounds times the distance for it, and we'll say that this distance is twice 9 inches, or 18 inches. Okay, so now I need to figure out what is my bicep weight. That's going to be 90 plus 180 divided by 2. That's 270, that's 135 pounds. So the point of this is that the force that's going on here in your bicep is a lot more than the force that we have out here. Of course, this is because this is what type of lever? It's not a class 2 lever. It's definitely not a class 1 because the axis of rotation is at the end. This is going to be a class 3 lever because I have my effort there, or I have my resistance here, and I have my effort right here. A very inefficient class 3 lever, by the way, because this moment arm is so small. All right, let's look at the dumbbell lateral raise with a 10-pound dumbbell. I want to estimate the force exerted by the deltoid in order to hold up the weight of the arm. So this is made more difficult because I have my deltoid muscle at the point of insertion acting at a very shallow angle. So if I draw a cartoon version of this, this is my axis of rotation. Let's see, I actually draw my axis of rotation the other direction. So this is like my axis of rotation there, like right up in his armpit. And then I have the dumbbell out here. So I have let's say I have a 5 kilogram mass. So I have a 50 Newton mass. That's the dumbbell, 50 Newtons. Remember, a Newton is about a quarter pound. So this is about a 10-pound dumbbell. And then I, um, I have the weight of my arm. And I'm going to go again with a 50 Newtons. So this is the weight of the arm right here, 50 Newtons. And now I have the force of the deltoid, and the deltoid is going to be right about here. Notice that I've done something different here, where I've not drawn it so that it's perpendicular, but I've drawn it so that it's some angle. And we'll just estimate that angle, and we'll say that, I don't know, 20 degrees. It's actually quite a bit smaller than that, but it'll make a point here. And then this distance right here is going to be about 10 centimeters, not very far. And then this distance will be 30 centimeters, and then we'll say that this distance is another 30 centimeters, so 60 centimeters. Okay, so now what we have here is I want to compare these two torques to this torque, and I want to figure out now what is the force of the deltoid. So on the one side, I have the force of the deltoid times my 10 centimeters will equal to the 50 newtons. This is the dumbbell, so it's 60 centimeters plus 50 newtons times, this is the weight of the arm, so that moment's arm was 30 centimeters. Let me just make sure we're clear on what I have here. So I have the force of the deltoid is right there. This is the weight of the arm, and then this is the weight of the dumbbell, and those are represented here in my cartoon version. Then I want to solve this for FD. If I solve that for FD, this is going to be 50 times 60 is 3,000 plus 50 times 30 is 1,500. And so FD is equal to 4,500 uh, divided by 10 is 450 newtons. So to lift the weight of your forearm plus a 10-pound dumbbell requires about 450 newtons. Just to give you some perspective, a person has a mass or weight of about 700 newtons. So your deltoid has to be a pretty strong muscle, and in fact it is, it's a pretty big muscle, to lift even just moderate weights. And that's because, again, this is a class 3 lever in your body, and then also, oops, oh no, I didn't do that. So also another issue is that I have a sine term here. So I left that out, so 10 sine of 20. And let's see how that affects it. So before, that 450 assumed that your force was perpendicular. But if I do 4,500 divided by 10 sine of 20, I get 1,300 newtons. It's like twice the weight of a human being required to lift just your forearm. That's pretty remarkable when you think about it, that we have these class 3 levers in our body that are terribly inefficient and that require very large forces to just pick up very small things. Actually, the forces inside of the muscles, those tension forces in the muscles. It's remarkable, human body.